Bismillahirrahmanirrahim. So we have been doing the principle of mathematical induction, the chapter 8. We described the first principle of mathematical induction where we haven't said that we should start after, we can have examples where we should start after some particular value, that it's not going to be, n is not going to be, n is equals to 1 is not going to be always the starting point. So for that, we have given some, what, like, we have improved this, and then we say that, let's say k be an integer, and then we can start by n can be greater than or equal to this k, and then we can say. Similarly, we have given some examples for that, and then we say that, like in this example, 2 power n less than or equal to n factorial, p of 1, p of 2, and p of 3 are false. So while p of 4 and 5 are true, so we should start n is greater than or equal to 4. Examples like this can be dealt by that modified second principle of mathematical induction. Now, the topic would be guess the answer. Guessing the answer, because there will be some problems which cannot be immediately be tackled using the induction, but first require some intelligent guesswork. And to understand this, we can talk about using an example. So let's say this is example 5. Find a formula for the sum. Find a formula for the sum. Which sum? The sum is 1 over 1.2, 1 multiply 2, 1 over 2 multiply 3, dash, plus 1 over n into n plus 1. Now, to answer this, we need to calculate this for few values. So of n. So let's say for n is equals to 1, this will be 1 into 1 over, this will be 1 into 2, which is 1 half. For n is equals to 2, this will be 1 over 1 into 2 plus 1 over 2 into 3. This is 1 half plus 1 over 6, which is 2 over 3. And for n is 3, this will be 1 over 1 into 2 plus 1 over 1 over 2 into 3 plus 1 over 3 into 4. And this is 3 over 4. So we intelligently spot a pattern in these answers and guess the sum of n terms is going to be probably the sum of n terms is n over n plus 1. Hence, we let P of n be the statement. Now we can write the statement n, which is 1 over 1 into 2 plus 1 over 2 into 3 plus 1 over 3 into 4 plus 1 over n into n plus 1 is n over n plus 1. This is the statement. And now we can prove this, that P of n is, now we attempt to prove P of n is true for all n greater than or equal to 1 by induction. So first, P of 1 is true. P of 1 is true, is noted, which is just 1/2, so that's fine. Now assume P of n is true. So 1 over 1 into 2 plus 1 over 2, 2 into 3 to 1 over n into n plus 1 is n over n plus 1. So adding 1 over n plus 1 into n plus 2 to both sides gives what? That 1 over 1 dot 2 plus now this adding, if you solve it properly, you will get here that after all of the things, you will get n plus 1 over n plus 2. And by this, you can say that P of n implies P of n plus 1. So P of n is true for all n greater than or equal to 1. Now see, it's very hard to write all of this expression from this side. So to do that, we use a notation. To make it simple, we use a notation called the sigma notation. Before proceeding with the next example, we introduce an important notation for writing down sums of many sums. So let's say if f1, f2 up to fn are numbers, then we abbreviate their sum as follows. We use this notation sigma, where we have r is starting from 1 up to n, and then it will be fr. The sigma is a Greek capital letter and is often called the sigma notation. For example, this fr, which is going to be 1 over r into r plus 1, is nothing but can be opened is 1 over 1 dot 2 plus 1 over 2 dot 3 plus 1 over n into n plus 1. So we can write this is r 1 to n 1 over r into r plus 1. Right? Okay. And then for example, 5.1 says And this says that in general, this is nothing but n into n plus 1. Now, for the first example, which was that you have sum of the odd integers is n square. First odd n integers is n square. You can write something the 1 plus 3 plus 5 plus up to 2n minus 1. And this notation can be written as r 1 to n into 2 power 2n minus 1. Not n, but you will have right r. This is n square. This is just an example. And you can also write this notation as if you can multiply the constants to it and then can add these sigma terms. So you can write notice that if A, B, C are constants, then you can say something like this: R is 1 up to n, A F R plus B GR plus C, and that means A into sum R1 to n FR plus B into sum R1 to n GR plus C into n. This could be the, and the left hand side, this left hand side, this can be opened as A into F1 plus B into G1 plus C. And this goes up to A into Fn plus B into Gn plus C. And you can write this as A into F1 Fn plus B into G1 up to Gn plus C n times. So that's how you connect these two equations. Okay, perfect. Let's give an example. Number 6 says that find a formula for some R1 to n R. This is something which is saying that sum of n integers. Okay, find a formula for that. The answer could be, we denote Sn for the sum, and for by example 1, which we have is written in the start of this lecture, in this chapter, which says that for R1 to n, sum of 2n minus 2r minus 1 is n square. So we can say n square is nothing but r is 1 to n 2r minus 1, which is 2 into some r1 to n, sum of r minus n, in which we can write 2 into Sn minus n, because this sum is equal to this term is Sn. So we can write, hence we can write that Sn going to be 1 over 2 n into n plus 1. And this is the sum of first n positive integers. Sum of first n positive integers. Okay, right. We can also write another example which says that find a formula for 1 to n r square, and this is asking you to find something like this: the sum of first n, the squared sum of first n integers. And to solve this, so we first try to guess the answer intelligently. The first few values for n, 1, 2, 3 gives the sum. Wow. For n 1, 2, 3, 4 gives sum is 1, 5, 14, 30. For n is 1, it is 1, for 2, it's 5, for 3, it's 14, and for 4, it's 30. It is not easy to guess a formula from these values. So yet done more intelligent is required. So the sum we are trying to find is the sum of n terms of quadratic nature. So it seems reasonable to look for a formula for the sum which is cubic in n, Say an cube plus bn square plus cn plus d. What about these? A, B, C, or what? What are they? Well, they have to fit in values with the values of the sum for n 1, 2, 3, 4, and hence must satisfy the following equations. Which equations? If you want to write this, some expression like this, you can write that you have to check it for n is equals to 1. It is going to be 1, which is nothing but a plus b plus c plus d and then n is equals to 2. They are going to be 5 is equals to 8a plus 4b plus 2c plus d. For n is equals to 3, this is going to be 14 equals to 27a plus 9b plus 3c plus d. And for n is equals to 4, this is going to be 30 equals to 64a plus 16b plus 4c plus d. And this is 1, 2, 3, 4. These are the question number 1 numbers. Now subtracting 8.3 by doing so everything. So let me write that. Subtracting 1 from 3 and 3 from 4, not 4. Sorry. Wait. 1 from 2, 2 from 3, and 3 from 4. we obtain another one, which is 4 is 7a plus 3b plus c, which is 19a plus 5. Let me cut these from here and put it here. Let me clear it here. We get another one, which is 19a, 5b plus c, and then 16 is 37a plus 7b plus c, and subtracting of these gives subtraction of these gives 5 is 12, a plus 2b, 7 is 18a plus 2b. Hence we get a is 1/3, b is 1/2, c is 1/6, and d is 0. So we get what? We get r is 1 to n r square is nothing but 1/3n cube, 1/2n square, 1/6n, and this can be written as 1/6n into n plus 1, 2n plus 1. Perfect. And this turns out to be correct. And we leave it to the reader to prove it by induction. Perfect. Thank you so much. And the next, we want to talk about a very interesting example, and then we can talk about the prime factorization.